Everyone, my name is Arsheen Shabir. Today we are going to see the topic theory of equilibrium. So what is equilibrium? Let's see the definition. A body is said to be in equilibrium if the net force on the body is zero. Means if we apply the force on a body and then the sum of all the forces on the body is zero, then the body will be said to be in a state of equilibrium. There are some types of equilibrium. Let a body be slightly displaced from its position of equilibrium is said to be, there are three types of equilibrium: stable, unstable and neutral. What is stable equilibrium? If the forces acting on a body bring it to the original position, then the body is said to be in stable equilibrium. If the forces acting on the body bring it away from the original position, then the body is said to be in unstable equilibrium. Neutral equilibrium: if the forces acting on the body remain it always in the position of equilibrium, then the body will be said to be in a state of neutral equilibrium. Let's understand it clearly by the example of a bowl and a ball. A ball kept in a bowl will be in the state of stable equilibrium because it will not move in any direction, it will in the same place only. And if we place the bowl in inverted direction and place a ball above it, then the ball will displace its position in any other direction. Then the state will be called unstable equilibrium. And a ball kept in a plane surface will act as a neutral equilibrium because it will not change its place. Now let's see the test for determining the nature of the stability. Let Z be the height of center of gravity of a body from point of contact. Express Z in terms of a variable theta. Then the position of rest is given by dz by d theta is equals to 0, which on solving gives values of theta, that is alpha 1, alpha 2, alpha 3 and so on, as the position of the equilibrium. There are some conditions for equilibrium to be stable, unstable and neutral. The first condition is the equilibrium is stable at theta is equals to alpha 1 if d square z by d theta square is greater than 0 at theta is equals to alpha 1. This is our sphere and the center is O and Z is this distance, G is center of gravity. The equilibrium is unstable at theta 2 is equals to alpha 1 if d square z by d theta square is less than 0 at theta is equals to alpha 1. However, d square z by d theta square is equals to 0 and for theta is equals to alpha 1, then we consider d cube z by d theta cube and d 4z by d theta 4. Third condition is for position of rest d cube z by d theta cube, the equilibrium is stable or unstable according as d 4z by d theta 4 is greater than 0 or less than 0 at theta is equals to alpha 1. There is a note: if z represents the depth of center of gravity of the body from some fixed original plane, then the equilibrium is stable if d square z by d theta square is less than 0 at theta is equals to alpha 1 and unstable if d square z by d theta square is greater than 0 at theta is equals to alpha 1. Now there are some general conditions for stability of a body resting on another body. When a body rests on another body, as we can see in the figure, there is a larger sphere and another body is kept on it, over it, where h is the height of center of gravity of upper body from the point of contact, and the radius of larger sphere is capital R and radius of a smaller sphere is small r. So the first condition is the equilibrium is stable if 1 by h is greater than 1 by small r plus 1 by capital R. The equilibrium is unstable if 1 by small h is less than 1 by small r plus 1 by capital R, where h is height of center of gravity of upper body from point of contact. Virtual work. What is virtual? Virtual means imaginary. So virtual work means imaginary work. So the formula of work is force into displacement. In case of virtual work, the force is actual and displacement is imaginary. That is, work is equals to force into displacement in the direction of force. If the force and displacement are in the same direction, then the work will be positive, and if the force and displacement are in opposite direction, then the work will be negative, which we all know. So what is the definition of virtual work? Virtual work is a work done by a force on a body or particle due to small virtual displacement. As I have told you earlier, force is actual and displacement is imaginary in case of virtual work. Now let us see principle of virtual work. If a body or a system is in equilibrium under the application of many forces, then the sum of all virtual work done by all the forces due to virtual displacement of point of application must be equal to 0. This is the principle of virtual work. Let us consider a rigid plane body in equilibrium. This is the rigid body and some forces are acting on it. Force F1, F2, F3 and F4. These forces are acting in different direction. The force F1, this is the point of application, that is from where the force is applied. This is point of application of force 1, this is point of application of force 2, this is 3 and this is for 4. So now if we take displacement, then in case of force F1 let us take example that the body is displaced through this displacement ds1 and this force is displaced ds2 and this is ds3 and this is displaced to ds4. So these are the displacement. The body will not be deformed, it will be only displaced. We will assume that it is displaced. Now in case of force F1, work will be W1, which is given by F1 ds1. In case of force 2, work will be W2, that is F2 into ds2. This is force into displacement, the formula of work. In case of force 3, work will be W3, that is F3 into ds3. In case of force 4, the work will be W4, that is F4 into ds4. So the total work on the body will be given by, on any body will be given by sum of all the forces, that is F1 ds1 plus F2 ds2 plus F3 ds3 plus F4 ds4 and so on, if there are other forces also. So according to principle of virtual work, the work will be 0, as we have read as we have seen. So according to the principle of virtual work, the work will be 0 on any body, as we have seen in the definition. So F1 ds1 plus F2 ds2 plus F3 ds3 plus F4 ds4 will be equal to 0 on any body. So if all these forces will be, if all these work will be positive, then the total work will not cannot be 0. There must be some positive and negative work. Then only the total work can be 0. So if we assume these two work will be positive and these two work will be negative, then only this can be equal to 0. As we have seen in this rigid body, there are some forces in the direction of in the inward direction and some forces in the outward direction. So this will be we have seen if force and displacement are in same direction, then the work will be positive, and the force and displacement in opposite direction, then the work will be negative. So we can say that all this work cannot be will not be zero. Some of them will be positive and some of them will be negative. This will give 0 on summing up these. So all work should not be positive, some should be positive and some should be negative. This was the principle of virtual work. Applications of equilibrium on strings. When a uniform string or chain hangs freely between 2 points not in the same vertical lines, the curve in which it hangs under the action of gravity is called catenary. If the weight per unit length of the chain or string is constant, the catenary is called uniform or common catenary. Now the equation of common catenary. Let ACB be a uniform heavy flexible cord attached to a point A and B at the same level, C being the lowest of the cord. Draw CO vertical, OX at OX horizontal, and take OX as x-axis and OC as y-axis. Let P be any point of the string so that the length of the arc CP is equal to S. Let W be the weight per unit length of the chain. Consider the equilibrium of the portion CP of the chain. The forces acting on the arc, forces acting on it are: first one is tension T0 acting along the tangent at AC and which is therefore horizontal. Tension T acting at P along the tangent at P, making an angle psi with OX. Third one is its weight WS acting vertically downward to the center of gravity of the arc CP. For equilibrium, these three forces must be concurrent. Hence, the line of action of the weight WS must pass through the point of intersection of T and T0. Dissolving horizontally and vertically, we have T cos psi is equals to T0, that is equation 1, and T sin psi is equals to WS, equation 2. Now, dividing equation 2 by 1, we get tan psi is equals to WS by T0. Now it will be convenient to write the value of T0, the tension at the lowest point, as T0 is equals to WC, where C is constant. This means we assume T0 to be equal to the weight of the unknown length C of the cable. Tan psi is equals to WS by WC is equals to S by C. C is equals to S is equals to C tan psi. This is equation of intrinsic. This is intrinsic equation of catenary. Now we will find the Cartesian equation of the catenary. We use equation 4 and relation dy by ds is equals to sin psi and dy by dx is equals to tan psi, which are true for any curves. Now dy by d psi is equals to dy by ds dot ds by d psi. Sin psi d by d psi is c tan psi equals to sin psi c sec square psi is equals to c sec psi tan psi. Y is equals to integration of c sec psi tan psi d psi plus a equals to c sec psi plus a. If y is equals to c when psi is equals to 0, then c is equals to c sec theta plus a, where a is equals to 0. Hence y is equals to c sec psi, that is equation 5. Therefore y square is equals to c square sec psi is equals to c square 1 plus tan square psi is equals to c square plus s square. This is equation 6. Dy by dx is equals to tan psi. tan psi is equals to S by C. S by C equals to under root y square minus c square by c. Hence dy by under root y square minus c square is equals to dx by c. Now integrating cos h inverse y by c is equals to x by c plus b, that is y is equal, if y is equals to c and x is equals to 0, y is equals to cos h x by c. This is our Cartesian equation of the catenary. Now system of forces. A force system is a collection of forces acting at a specified locations. Thus the set of forces shown on any free body diagram make up a force system. Force system is simply a term used to describe a group of forces. So this was the force system. Now conditions of equilibrium of a rigid body. If the forces F1, F2 till F1, if till Fn are acting at A1, A2 and so on respectively on a body, so we can reduce the system into a single force R acting at an arbitrary point O and a couple having moment G, couple moment G, whose axis passes through O. Now some definitions. First one is point-sort central axis. What is point-sort central axis? A line through a rigid body which is parallel to a vector sum F of a system of forces acting on the body and which is located so that the system of forces is equivalent to the force F applied anywhere along the line plus a couple whose torque is equal to the component of the total torque T exerted by the system in direction of force. Second definition is central axis. If a system of force reduced to a single force and a single couple in such a way that the axis of a couple coincide with the line of action of force, then the line is called the central axis. Wrench and pitch. If a system of force is reduced to a single force R and couple having moment K whose axis coincides with the direction of force, then RK is called the wrench of the system. Ratio R by K is called the wrench of the system and the ratio K by R is called the pitch of the system. Now screw. What is screw? A straight line along with the acting force when considered together with the pitch is known as screw.